as we've just seen, our numerical representations can get really, really big. And so what I'm going to tell you about now is an issue that's even more fundamental and important, and that's something called integer overflow. So it turns out in Java, there is a biggest possible number. And in particular, that number is 2,147,483,647. And if you go over this number, you overflow, which means you start back over at the smallest number. So in other words, if I write a program where I set x equal to the biggest number, and I print out x plus 1, I get the smallest number. So that's the number that comes after the biggest number is the smallest, and that's actually really, really important when it comes to us trying to come up with integer representations of arbitrary data. So because Java has a maximum integer, when we're calling our function like ASCII to int or English to int or whatever, we're going to run into overflow. So for example, omens in base 126 is 28 billion, which is way bigger than the maximum integer, which is only around 2 billion. So instead, this will overflow many times, and it'll eventually settle down at negative 1.8 billion. Okay? So we would expect 28 billion, but we get negative 1.8 billion, and that's going to be an issue we need to take to heart. So and I think maybe most fundamentally, the issue is that we will get collisions even when we shouldn't. So as I said earlier, ASCII to int gives a unique value for every possible ASCII string. But here, if I create a data indexed integer set and I add in melt banana, and then I say, hey, do you contain subterrestrial anti-cosmetic, I will get true. And the reason is that if I take into account overflow, these two strings end up having the same exact resulting value. So the official term for the number that we're computing, and I might have accidentally said it earlier even, is hashCode. And I'm borrowing this definition from Wolfram Alpha. So a hashCode projects a value that is in a set with many or even infinite members down to a value from a set with a fixed number of members. So in this case, our target set, the thing that we're projecting to, is Java integers, and there are 4.29 billion of those. So we go from a space of infinite possible strings to this relatively small set of only 4.3 billion, much smaller than infinity. So these hashcodes, we're just guaranteed to have collisions because of something known as the Pigeonhole Principle. So the Pigeonhole Principle says that if there are more than 4.3 billion possible items, well then multiple items need to share the same hash code because there's only that many different values in our target set. And it's inspired by this picture here of a bunch of pigeons in boxes. So here there are 9 boxes and 10 pigeons, and no matter how you arrange the pigeons, it's guaranteed that at least one box is going to contain more than one pigeon. Okay? And so here, just to make that very explicit, there are more than 4.3 billion-ish possible planets, because each planet has a mass, an x position, a y position, an x velocity, a y velocity, and maybe an image name from a planet simulation project from this class. Now, there's also, of course, more than that many strings. We can have the string for the word 1, 2, 19 quadrillion, and so forth. So it's just guaranteed we absolutely will have collisions as a fact of life because of integer overflow. So we're left with 2 fundamental challenges that we're going to try to address for the rest of this lecture. The first is, how do we resolve these collisions, say melt banana versus subterranean anti-cosmetic, and we'll call that collision handling. The other is, how do we compute a good hash code for arbitrary objects? And we're going to spend most of our time on this first challenge, but we'll say a little at the end on the second. And as I said, we call this computing a hash code. And so for example, our hash code for melt banana was this 839 million number. And for strings, what we saw so far, this was straightforward. We treat it as a base 26, base 126, base 27, base 40,959, whatever we might want to do. And so those will be the fundamental challenges we will try to address moving forwards.